Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory combinatorics based on my book, An Invitation to Combinatorics. The subject of this lecture is combinatorial proofs of binomial identities, identities of binomial coefficients, but proving them combinatorially. So first of all, what is a combinatorial proof? Basically, there's two ways of doing a combinatorial proof as opposed to other kinds of proofs. One is you take the same set and you count the size of it in two different ways. And when you can do that, if you can do different ways, then you get two different expressions for the size of the same set. And those two expressions got to be the same. And then you've got yourself an identity. This guy got to be equal to that. Why? Because they both count the size of the same set. If you do that, then you've done a combinatorial proof of that identity as opposed to using formulas and so forth. Another way would be to have two different sets and find a bijection between them. A bijection is a one-to-one onto map from one set to another. I've got videos on those. You might want to watch if you're not familiar with one-to-one onto functions. And when you find a one-to-one onto function from one set to another, you're saying that they have the same size if they're finite. Even if they're not finite, you're saying that there's a one-to-one correspondence between them. You're matching the elements of the two sets. And therefore, if you have some idea of what the size of this set is and the size of that set is, now you have proved that they have the same size. And that can lead to a identity as well. Now, in this lecture, we will be focused on binomial coefficients. So what are those? N and K are integers, and we've seen these in previous videos when we talked about combinations and so forth. We have already talked about binomial coefficients, but I'm going to remind you. N and K are integers, and K is between 0 and N inclusive. And we use the notation bracket N for the set with N elements. Basically, we just want a set with N elements, and this is our stand-in for that set. That's set 1, 2 through N. And for convenience, we'll say that the bracket 0 is the empty set. The binomial coefficient N choose K, we read this parentheses N and K on bottom as N choose K, is the number of K subsets of bracket N, the number of subsets of size K of a set with N elements. K subsets means subsets of size K. So if N is 47 and K is 5, then N choose K is how many subsets of size 5 does a set with 47 elements have? And in fact, in our previous videos, in the video on combinations, we came up with a formula for this N choose K. It's N factorial divided by K factorial over N minus K factorial. And so we can generate these numbers as we like, and these numbers are called binomial coefficients for reasons to be clear in actually the next lecture after this one. These numbers have all kinds of patterns, and those translate to identities about these numbers. There's all kinds of identities about these binomial coefficients, and the purpose of this lecture is to convince you that we can prove some of these without using the formula, without getting our hands dirty with the formula. The combinatorists like me really like combinatorial proofs, when you prove things without too much calculations, but conceptually. So here's the table of binomial coefficients. We have an N, the size of the set, and K, the size of the subsets. So for example, this 10 here tells you that if you take a set with 5 elements and look at for how many subsets of size 3 it has, the answer is 10. A set of 5 elements has 10 subsets of size 3. 5 choose 3 is 10. Usually this table is not written in this format, but written as a triangle. And so when n equals 0 is the top row, then n equals 1, n equals 2, n equals 3, 4, and 5, and so forth. Every row tells you what n is, the size of the set is. Every column tells you what k is. In every row, k starts with 0, then 1, then 2, then 3, then 4, and then 5. And so, for example, the entry in row 5, column 2, when we say row 5, remember that we're starting with row 0. And when we say column 2, in that row, we're starting with column 0 as well. The entry in row 5, column 2 is 5 choose 2 and happens to be 10. and that's the number of ways to choose 2 objects out of 5. How many subsets of size 2 has a set with 5 elements? If you have 5 people, how many committees of size 2 can you make out of them? And the answer is 2. This table most commonly is known as Pascal's triangle. Most people call this Pascal's triangle. It's more apt to call it Karaji-Jia, Bashkara, Yanhui, Khayyam, Ben Gerson, Tartaglia, Pascal triangle, because this triangle, Pascal did work on it in the 17th century and wrote a book that was pretty modern in its format, and covered these things. He didn't call it Pascal's triangle. A couple of centuries later, in the 18th century, French mathematicians started calling Pascal's triangle. But this triangle, its properties, and working with it was known at least 600 years before Pascal, all over the world, in China, in India, in Iran, in the wider Islamic world, in Northern Africa, in the Hebrew tradition, and in Southern Europe. It was known much before the Pascal. Different people thought about it. In India, for example, people were interested in combinatorial counting problems, whereas in the Islamic world and in Iran, people were mostly interested in the binomial coefficient aspect of it, but also combinatorial problems. But the set triangle was known. I like to call it the Karaji-Jia triangle, because the oldest actual triangles that have survived are from these 2 folks. So here is a page of a document, or a part of a page of a document from the Süleymaniye Library in Istanbul. This document itself is from the 14th century, but it's a copy of a book by al-Samawal from the 12th century. But in it, he explains that this table and this way of thinking of binomial coefficient is due to al-Karaji, Karaji in Persian, who was someone from Karaj, not far from my hometown of Tehran. So sort of shout out to homeboy here. Karaji, to do Karaji, circa the year 1000, so about 600 years earlier than Pascal. This particular picture is from my book. Here's another version from China, and this one is due to Jia Shan, who did this about 50 years after Karaji. Again, we don't have his manuscript is not extant, but through other manuscripts, ones done by Yang Hui, or in this case, the one that I'm showing you by Zhu Shij, we are familiar with the triangle that he made. This one is from the 14th century, but again, these are reporting on Jia's triangle earlier. And so, because I like these 2 manuscripts, I am going to call the triangle the Karaji-Jia triangle, as opposed to Pascal. It's not the final word, not necessarily the correct way of calling it, and the judgment is still out what it really should be called. But what's clear is that working with this triangle was something that has been done all over the world globally much before Pascal. Okay, so we want to now find patterns in this in this table of binomial coefficients, and we see some. Like, for example, we see the symmetry in each row. Like, if you look at that 8th row, again, rows start with 0, go down to 8. The 2 extremes are 1, and then as you come in, you get 2 8s, and then 2 28s, and 2 256. There's this symmetry, and that happens in every row. And why is that? And actually, we have in a previous video, we had 3 proofs of this, but I'm going to quickly give you a combinatorial proof. So n and k are non-negative integers. K is less than or equal to n. Why is it that n choose k, which is the entry in row n column k, the same as the entry in the same row, but in column n minus k? So k is k units from the left, n minus k is k units from the right, and we're saying these are the same. And the proof is pretty straightforward. N choose k counts the number of subsets of size k of an n set. Well, take a subset of size k and match it with its complement. So here you have subsets of size k, here you have subsets of size n minus k. This identity telling you the number of subsets of size k and n minus k of a set with n elements are the same. Why is that? Well, match them. Match every subset of size k with a subset of size n minus k. How do you do that? Well, you match everything with its complement. If you have a subset of size k, its complement will have a subset of size n minus k, and vice versa. A complement of a set of size n minus k is a set of size k. So matching something with its complement is a one-to-one onto map. It's a bijection, and it tells us that there's as many subsets of size k as there are subsets of size n minus k, and that means that n choose k is the same as n choose n minus k. Again, we did this without any calculation, although if you knew the formula, then it would be obvious from the formula, but we don't like to do that. So here's another one, that's sort of an obvious one, which is the recurrence relation. So if you look at that 10, where one way to think of it is that is the sum of the 6 and 4, the 6 and 4 right above it. Where's that 21 come from? Well, it's the sum of the 6 and 15 above it. You might say, well, that's actually, isn't that the way we define this Karaji-Jia triangle, also known as Pascal's triangle, that you add two terms and you get the one below that? Not really. The definition I gave, I mean, you could define a triangle that way, but then you have to decide why is that this triangle tells you anything about the number of committees that you can, committees of size 3 that you can make out of 5 people and so forth. The way I defined binomial coefficients is that they're the number of subsets of size k, and now I have to show you that actually if I put them in this triangle, that every entry is the sum of the ones above it. And so how do I do that? So what I want to show is that n choose k, the number of subsets of size k of n, is n minus 1 choose k plus n minus 1 choose k minus 1. Now, n minus 1 choose k and n minus 1 choose k minus 1 are both on a row above n choose k because their n is one less, and their k's is one the same and one less, and that makes them the one right below it and right after it when we write them in that format of a triangle. So we want to know what that is. And again, we do a combinatorial proof. We say that n choose k is the number of subsets of size k of a set with n elements. These subsets come in two varieties. They either contain n or they don't. Any subset of size of any size could contain n. N is one of the elements of 1 through n, or not. And subsets of size k are no exception. Now, how many do not contain n? How many subsets of size k does 1 through n have that do not have n? Well, if they don't have n, then there are subsets of size k of n minus 1. And by definition, the answer is n minus 1 choose k. So there's that many subsets of size k of 1 through n that do not include n. But that's not all. How many of them do contain n? Well, if you have n in your subset and you want a subset of size k, then you've got to put another k minus 1, but you put the k minus 1 out of the n minus 1 remaining elements. And so the number of ways of doing that is n minus 1 choose k minus 1. Subsets of size k minus 1 of a set with n minus 1 elements, because you're ignoring n. And so because of that, the total number is going to be the sum of these, because again, any subsets of size k either includes n, there's this many of them, or doesn't include n, and there's that many of them. And if you add them, you get the total number. Okay. Now here's another question, which is that what happens when you add the elements in one row? N choose 0 plus n choose 1 plus n choose 2 plus n choose n. You should stop this, stop the video, go look at the table, see what the answer is, and I mean, like, do some rows and try to guess what the answer is, and then give a combinatorial proof. And if you got it, then you can just fast forward. If you didn't, then you can listen to this. But working it out yourself for all of these things is a much better idea than listening to me. So the way we're going to do this is, instead of actually writing formulas or anything, we're going to say, what does this count? And after knowing that, can we count whatever that is differently? So what is n choose 0? N choose 0 is, well, n choose k is the number of subsets of size k with a set with n elements. So what am I doing there? I'm saying how many subsets of size 0 a set with n elements have, how many subsets of size 1, size 2, size n, and then adding them. So I'm taking this number of subsets of size 0 plus number of subsets of size 1 all the way to the number of subsets of size n. When I add those, what I'm really getting is the number of all subsets of a set with n elements, because I'm just counting them slowly. Instead of saying how many subsets does a set with n elements have, I'm saying, well, how many subsets of size 0 it has, how many subsets of size 1, size 2, size 3, all the way till size n, and then adding them. Well, that's the same as telling me how many just subsets of any size this set with n elements has. And that we know. What is the answer? Well, how many subsets a set with n elements has is 2 to the n. Why is that? Well, because the way to make a subset is to say element number 1, 1. Is it in or not? I have two choices. I can either put it in or not. Element 2, is it in or not? Again, I have two choices, and that's independent of the previous ones. So far, I have 2 times 2 choices. Putting 1 in and 2 in both, putting 1 in but not 2, not putting 1, putting 2, and not putting either. And then you just continue like that. You have 2 choices for 3, 2 choices for 4, all the way till 2 choices time for n. So that's 2 times 2 times 2, all the way times 2, multiplication principle. If you're not familiar with that, watch my video on the multiplication principle. You get 2 times 2 n times, and that's 2 to the n. So we just proved that when you add the entries of one row, you get 2 to the n. Sometimes we can actually come up with identities using thought experiments, by sort of thinking up some stuff. So let's see. So for example, you can say I have a set with 2n elements. I just made that up. You could have 3n elements and come up with your own identity if you like. I have a set with 2n elements, and I want to know how many subsets of size n does it have. Well, I know the answer to that. The answer to that is 2n choose n. So what? But I'm going to now try to count this in a different way. And this is what I'm going to say. I'm going to count it differently. How? Well, the elements of S, think of them as people. I'm going to ask n of them to wear red hats. So you've got 2n people. You're going to choose n people. But now among your 2n people, n of them are wearing red hats. And so instead of picking just n elements from the whole group of 2n people, which the answer would be 2n choose n, that's the number of ways I could do that. Instead, what I'm going to do is I'm going to say, first I'm going to pick some people who are wearing red hats, and then I'm going to pick some people from the people who are not wearing a red hat. And that's how I'm going to make my subsets of size n. Now, how many people with red hat could I pick? I could pick 0. I could pick nobody with a red hat and just pick all my n from the rest. Or I could pick 1 person with a red hat, or 2 people, or 3 people, or k people in general, or all the way to I could pick all the n people with red hats and nobody with not a red hat. So, so I want to choose a total of n people, but k of them wearing red hats. How do I do that? Well, the number of possibilities is going to be n choose k, because from the n people with the red hats, I've got to pick k. But then I want the whole group to have the people I chose to have n people out of the 2n people. So from the people who are not wearing a red hat, which are n of them, I have to pick the remaining n minus k, because I've already picked k people with a red hat. I need another n minus k people so that together I get n people. So I have n choose k, that means k people with red hats, and n choose n minus k, which is n minus k people without a red hat. And I multiply those because, again, multiplication principle, and that's the number of possibilities. If I want to pick k to n people, but I want to make sure k of them have red hats. But it doesn't have to be k who have red hats. It could be 0, it could be 1, it could be 2, it could be n. And so I have to do that multiple times with 0 people with red hats, 1 people with red hats, or n people with red hats, and I will get this total number. And so this is the total ways of picking a subset of size n. Instead of 2n choose n, I can do this. So this must be the same as 2n choose n. But I actually noticed that in each of these, the two terms are equal because of the symmetry principle. N choose 0 is the same as n choose n. N choose 1 is the same as n choose n minus 1. And out here, n choose n is the same as n choose 0. So really, this is n choose 0 squared, n choose 1 squared, n choose n squared. And I've just proved that the sum of the squares in a row is always 2n choose n. So this was also a combinatorial proof. So what are this? I'm done with my examples. I want to tell you some sort of a general idea of some of the future things we'll do. And then I'll tell you an open problem about a conjecture that hasn't been yet proved. No one knows how to prove about binomial coefficients. So n choose k was the number of k subsets of n. And how do we find identities for this? Well, we have used combinatorial arguments in this lecture. That's how the way we like to do things, using combinatorial arguments. But that's not the only way. We could also use the formula. N choose k is n factorial divided by k factorial or n minus k factorial. And sometimes that's the best way to prove things. In particular, in the next lecture, we show that these binomial coefficients are unimodal, like it means that in each row, the numbers go up and then come down and they don't change. I mean, that seems sort of, if you look at the table, that's obvious. But why is that actually? Using the formula is maybe the easiest way of proving that. You could also use induction and the recurrence relation that we proved using a combinatorial argument. Induction always likes recurrence relations, because if you have something that you want to prove about these binomial coefficients, and if you want to use it by induction, it really likes it if you can go to smaller cases. And this recurrence relation allows you to do that. So if you have something about binomial coefficients that you want to prove, this recurrence relation says n choose k is these guys, and these guys are the smaller cases. And then by induction, you might know something about them and prove that. And the final way is using something called the binomial theorem, which is the subject of a future lecture. And that's a way of using algebra and actually even calculus to prove things about binomial coefficients. And I won't talk about that here, but you will. And this is sort of a beginning of something called generating functions, and we will see that method later as well. So now to this open problem. So here's the question: other than one, I mean, if you look at the Karaji-Jia triangle, one appears an infinite number of times because every row starts with a one and every row ends with a one. Other than that, there are things that occur more than once, like 10 appears twice. We see that. And a number has so far a chance of appearing. After a while, the numbers are just going to be too big for it. But one question is that, is there any integer that appears in the table of binomial coefficients 1,000,000 times or more? So that's a question. Can you find a number other than one that appears 1,000,000 times or more in the table? And the answer is, we don't know. And we also don't know the answer if instead of 1,000,000 times, you say more than 8 times. Is there a number that appears 9 times, 10 times, or more? We don't know the answer. The current record holder is 3003 that does appear at 8 times. It's 3003 choose 1, 78 choose 2, 15 choose 5, and 14 choose 6. Well, that's 4 ways. What's 8? Well, by symmetry, it's also 3003 choose 3002. It's also 78 choose 76. Is also 15 choose 10, and 14 choose 8. So it appears 8 times, but we don't know if there's anything else. I mean, 3003, where did that come from? Is there any other integer that maybe appears 10 times? If you can find one, you will be famous, because then you will have moved our knowledge of these binomial coefficients further. The conjecture by Singmaster from 1970s, and people have thought about this and worked on this since then, but cannot figure out how to prove or disprove this conjecture, is that there is a constant upper bound on the number of times an integer other than 1 appears in the table of binomial coefficients. In other words, there's a number, maybe it's 8, that binomial coefficients cannot appear more than that. There's a fixed constant. Maybe it's 8, maybe it's 1,000,000. Who knows? We don't know what that number is, but some number that above that known number other than 1 appears more than that. This is the end of this lecture. If you like this, if you want to like and subscribe to this channel, and if you do, you will be treated or maybe subjected to more videos like this one. See you next time.